Welcome to this hands-on session. Today we will have a look at DFT. We will use two main tools. One is Quantum Espresso, which is our DFT engine. Other is ASE. ASE is a Python interface to set up, run and analyze the calculations. And our system example will be nickel oxide, that's NiO, in a small periodic box. With that one material, we will have a deep look into the typical DFT workflow using Quantum Espresso and ASE. The workflow will be like, we will load and visualize the NiO structure. Then we will perform geometry optimization, that's we will do atomic relaxations and cell relaxation. Then we will perform more accurate SCF calculation to get total energy and the Fermi energy. And finally, we will compute and plot electronic band structure. Let us get started. In the first cell, this will import main atomic simulation environment utilities and the Quantum Espresso interface. In the second cell, if we do ls, we can see we have mainly three four files here. One is our DFT notebook, other is the CIF file, that is the initial structure, and other two are the pseudo potentials for the nickel and the oxygen. In the next cell, we can read the structure. We can see we have atomic symbols like NiO4 and O4. And this is the cell dimensions 4.178, 4.178 and 4.178. To visualize the structure here, we can play around this structure and visualize this NiO structure here. And next, we will load the pseudo potentials. We can see which executable used in this calculation. This is the path of the executable pwx.x. And this cell, we can set up number of threads we will be going to use for this calculation. Then here the espresso profile is created to define how ASE should call Quantum Espresso. And this command specifies the path to pw.x for a single core run. And pseudo underscore dir tells Quantum Espresso where to look pseudo potential files. So this cell, we have the input data like the calculation type is VC relax, and pseudo directory is directory where pseudo potential files are stored, and other settings are here like restart mode, start run, ignore any previous restart data, and other settings are like total energy convergence threshold for relaxation, and other is force convergence threshold to stop relaxation. And other setting is like, if we see here, ncut, which controls the plane wave basis size, and the last one, the allow full relaxation, shape, volume and atomic positions. This cell initiates the magnetic moments of all the atoms. If we see here, we have Ni we have 4 atoms, and oxygen we have 4 atoms. We have initiated two mag moments for the Ni and 0 for oxygen. Here in this cell, an espresso calculator is instantiated for a structure relaxation step, and this profile tells ASE to run Quantum Espresso, path to pw.x, pseudo directory, etc. Pseudo potentials we have used here, we can be seen here, and k pointers we have 2 cross 2 cross 2, and the input data we have defined earlier here. Let's execute this cell now. Now this line structure.calc is equal to calc. This line attaches previously defined espresso calculator to the structured atoms object. Okay. This cell explicitly triggers the geometry relaxation calculation. So this structure.calc.calculate starts quantum espresso VC relax using the current structure and calculation settings. Okay. Now that once the relaxation is complete, this cell reads the relaxed geometry from the quantum espresso output file. Okay, we'll fast forward this step now. Okay, now the calculation is complete. Let's get the final structure, that the relaxed structure here. Okay, so let us save the output structure in the form of CIF file. Now that the relaxed calculation is done, we'll perform SCF calculation. For the SCF calculation, we need again now the input data here. As we had earlier here the input data, we need the input data here again for the SCF calculation. Let's execute this cell also. Now in the same manner as we have earlier done, we will have the new espresso calculator here, and only thing is we have new K points here. Earlier we have 2 cross 2 cross 2, now we have 4 cross 4 cross 4. In the same manner we can have the maximum values here for both nickel and oxygen. And now SCF calculator is attached to the relaxed structure here. Let's get the relaxed structure positions here and get the total energy of the structure. It may take a while. Okay, we'll fast forward this step now. We have got the total energy here, and let's get the Fermi energy level. That is 18.9309. For the band structure calculation, this line set up the ingredients for that. The lattice here gets the cell of the relaxed structure. The band path constructs standard high symmetry K point path to the Brillouin zone, and we have here 50 points along the path. The basic input data defines quantum espresso input parameters for a band calculation. Let's execute this cell. And here the calculator for the band structure run is created and attached. Okay. Now this cell runs the band structure calculation. Let's execute this also. It may take a while. Okay. Now the calculation is complete. Now the computed band structure data is parsed into using ASE spectrum utilities here. Execute this cell also. Now this cell here creates and displays the band structure plot, and it plots the bands in the energy window from 5 electron volt below to 5 electron volt above the Fermi level. The Fermi level we have around 18 point something, and we will plot the band structure here, and we can see here as DFT underestimates the band gap, and since NiO is actually the insulator and it predicts it as a conductive material because the DFT underestimates the band gap. So this is the end of the tutorial session here. Thank you.